a delta function. Okay, model this hammer blow response of a mass spring system. Yeah. So this time you can see the driving force. We model that hammer blow type force, yeah, impact type, yeah, initial values. Yeah. But when we do the calculations, so you can see the only difference is we just use a different formula for this part, yeah, delta function, this part. Yeah. And the calculation almost the same as before. Yeah. All right. Yeah, so that formula, derivative formula we are familiar with, and the initial value is 0, so that each term, the Laplace transform of first derivative, second derivative, each one has one term. Yeah, Laplace transform of the second one, this term, first one, 3 times one term. That, yeah, we apply the Laplace transform of the delta function, yeah, and a equals 1, yeah, a equals 1, yeah, so we get e to the negative s, and find the capital Y, yeah. The numerator we can split easily, yeah, so easier than our previous example, because the denominator only product of two factors. So one split, yeah, we can get it. Yeah. Then the second shifting theorem. Okay, yeah. But we need to yeah, negative s, negative a. Yeah. Yeah, but here, before you apply, you need to apply the first shifting theorem. Yeah. Here you can see you need to apply two shifting theorems here, yeah. First and second. Yeah. S, yeah. But you need to do shifting. This is the first shifting theorem. Okay, first shifting theorem. The second shifting theorem. Yeah. Yeah. All right, so let's do first shifting. Yeah, because we can, by the linearity, we can write that. You need to apply two shifting theorem. All right? Yeah. All right. Inverse Laplace transform is 1, then this 1 is little f, right? Yeah, that little f. Then minus a, this minus a equals negative 1. Okay? Yeah, this time a equals negative 1. Yeah. So you need to multiply e to the negative t. Yeah. So e to the negative t. Yeah. That's you apply the first shifting theorem. This place, you first shifting theorem. All right. Then, yeah, the second term, you also do the similar thing. Yeah, but your a equals negative 2. Yeah. Then, the numerator e terms, you put it back, so you need to apply the second shifting theorem. Yeah. All right. Yeah. So that is little f, because you know little f. Yeah. This is first little f. Little f. Okay? Yeah. That little f. Then you get that. The second little f. This is second little f. Then you do the shift. You do the shift, but when you do the shift, you only use the shift from this e function part. The shift. Oh, sorry, I need to. Yeah, right. Yeah, no problem. Yeah, because little f is different. Yeah, the shift the same by one unit to the right, but the little f function is different. All right. So then you put together, yeah. So you get a little y. Yeah. Yeah. So when you do the calculation, you should be, very careful. Yeah. You need to practice. Okay? You need to practice several times and get used to those two shifting theorems. Yeah. We need to frequently use these two shifting theorems. Yeah. So you need to, really build up some experience using these two shifting theorems. Yeah. All right, yeah? Then, four-terminal RLC network. Yeah. So it's a, electric circuit. But here, the difference, the four-terminal, okay? Two terminal here, yeah, and two terminals here, right? Yeah. One V function, V of t, little v of t, that function given, but the other one, it's a delta function, yeah, like that. Okay. All right. Then the R, L, C, all given, yeah, given, okay. Then we need to establish equations. Yeah. All right. Yeah. So here, so using the, Kirchhoff theorem, right? So using this circle, yeah, apply the Kirchhoff theorem on that circle, so you have that. Yeah, right? Yeah. Then you apply Kirchhoff theorem on this circle. Second circle, you have this V of t equals. Now, each circle you can apply that Kirchhoff theorem. Okay, yeah. Kirchhoff voltage theorem. Yeah. So you apply twice, you have two circles. Okay, two circles. Apply Kirchhoff theorems twice. All right. Then by solving, so here you can see, by solving the first equation, we can find the little q of t. Then we plug in the second one, we get v of t function. Yeah. All right. Yeah. So the first function we know, because little I is derivative of little q. Yeah. So we want to have a function with one unknown function. Yeah. Not two. Yeah. One unknown function. So little q function unknown. Yeah. Yeah. Because I equals q prime. Yeah. Then, yeah, we'll plug in the numbers. Yeah. So we get this equation. Yeah. All right. Yeah. Now we need to calculate Laplace transform. Yeah. So we put a formula here. Yeah. All right. Derivative formula and the initial values. Yeah. Current, charge, yeah. Initial values. Yeah. And here, yeah, because in this word problem, current, charge are 0 at t time. Yeah. Sometimes, some students, they do not know how to apply these initial conditions. Yeah, yeah, yeah. So that's a. Yeah. All right. So here, yeah, here let me say something about the initial condition. Current and charge q, little q, right? Yeah. Q of 0 equals 0. Yeah. The first initial condition. Charge I of 0 equals 0. Yeah. Because we know I equals q prime, right? This means, yeah, this means q prime of 0 equals 0. Yeah, so that's why when we apply the derivative formula, because this little f equals q here. Okay? Yeah. So all the terms using initial values all gone. Yeah. So that's why, yeah. So we have, you can easily see we have this equation. Yeah. All right. Yeah, because y right hand side is 1 because a equals 0, right? Yeah. When we apply, a Laplace transform of delta, a equals 0. Yeah. E to the 0, that's 1. Yeah. E to the 0 times s. So that's 1. Yeah. So you can find the q easily. Yeah. Then, to find the little q from this inverse Laplace transform of this capital Q, you need a sine function, right? Yeah. So here, sine function, omega. Shift, this is a shift. Okay? But omega squared, this is omega squared. So yeah. So then the shift function. We need these two formulas. Yeah. All right. But we need to apply the sine formula first. Yeah. Yeah, omega. So let's do the sine omega. Omega, yeah, so the number, you get this function. Yeah. But then shift. Yeah. Shift. So a, yeah, so what? A equals negative 10. Yeah. So a negative 10. So you multiply that. E to the at term. So that's the q function. Q function there, the v function, you can get it quickly. Yeah. V function just divided by capital C. Yeah. Yeah. So you solve this problem. Yeah. Here you can see, yeah, this word problem is not hard to solve. Yeah. Yeah. Sometimes, because many of you may feel, not easy to solve the word problems. Yeah. Yeah. But if you have the knowledge we need, yeah. So all these things, so Kirchhoff voltage theorem, and how to apply. Yeah. So here you have this example. Then Laplace transform, the appropriate formulas. Yeah. It's not that hard. Yeah. Yeah. All right. So I think this is so we complete the part B. Yeah. Next we can start new part, part C. Yeah. So we will learn some more important tools, methods about Laplace transform. Yeah. Yeah, let me get out of part B. Okay, yeah. Then part C. Differentiation and integration of Laplace transform. Yeah. C.1, convolution and integral equations. Yeah. Convolution operation. Yeah. First, I need to give you a short introduction about the special convolution operation. Yeah. All right. Yeah. The definition, but first, why we need it. Okay. Yeah. First, let's look at a simple property. Yeah. By the linearity, so this is the linearity principle of Laplace transform. Linearity, obvious, right? Linearity property. Yeah. All right. And the function whose Laplace transform equals the sum of the Laplace transforms. Yeah. Yeah. But from there, yeah, yeah. So here because we want to use this formula to give us some inspiration. Yeah, some inspiration. All right. Yeah. So here. I mentioned last time, some mathematicians, when they need to discover some new properties, so they need to have imagination. Yeah. But they also, with imagination, they need to get inspired from something. Yeah, here, yeah, from this one. All right. Then we want to look at a new question. Yeah. Laplace transform of what function equals the product of two Laplace transforms? Yeah, it's easy. Yeah, f plus g. Yeah. But for product, what should we have in that question mark place? That's the inspiration. Yeah. Yeah. If you can figure out what should we put in the question mark, then some new result is discovered, by those early mathematicians. That's a new result. Okay, something new. Yeah. Then they wrote a paper. Okay. Yeah. They're talking about this new property. Yeah. All right. Yeah. First, people want to see if it's a product of f and g. Yeah. Yeah. But usually not, right? Yeah. Usually not. Yeah. But first, yeah. So it's very easy to verify it. Yeah. Actually, it's very easy to verify. Yeah. It's not that. Okay. Yeah. Yeah. Because if f and g, if you use 1, it cannot be true, right? When you use f and g equals 1, it cannot be true, right? Yeah, because the Laplace transform of 1, what's that? 1 over s, right? Laplace transform L of 1 equals 1 over s. Okay? Yeah, the simple formula. Then this side should be 1 over s squared, right? Yeah. But 1 times 1, still 1. Laplace of 1, it is 1 over s. How can they be the same, right? They cannot be the same. So that must be wrong. Yeah. All right, then let's consider the convolution of two functions. First, give you the definition. Yeah. All right, we introduce a new function, h function, that is, because this is a special operation, we need a special notation. Yeah. Here we use this star to represent. It's not a product, okay? Yeah, in math, yeah, the star operation, it's not a product. Yeah. F star g, so we define as a new operation, yeah, convolution operation. And its definition, we use the integral. Yeah. Integral from 0 to t, then inside f of tau times g of t minus tau. Yeah. This special definition, the convolution definition. Yeah. All right. So here, so let me draw the, yeah. Try to understand the structure of the convolution. Yeah. 0. Then the t point. Okay, t point. Yeah. Here the t is fixed. Yeah. Here, when you look at it, when you understand the integral, we treat the t value is fixed value. Yeah. Because later we can imagine t is a variable. Yeah. But when we understand this integral, we fix the t value. Yeah. All right. So now you take the integral in this interval between 0 and t. Now, then you need to use a variable, dummy variable. This tau is the dummy variable. Okay, tau is the dummy variable. All right, tau can be anywhere in this interval, right? Yeah, tau from 0 through t anywhere in this interval. Yeah, let's select one arbitrary point. That's the tau point in this interval. Yeah. Then, when we use this g function inside the parenthesis, it is t minus tau. Okay? Yeah. So here you can see which point is t minus tau. This point. This point is t minus tau. Okay? So you can see these 2 points, they are symmetric. These 2 points, symmetric. Yeah. Yeah. There is some symmetry, okay? Yeah. So, the distance, the first point between the left and the distance the same as the distance second point between the right end point. Yeah. Symmetric. Yeah, so here you can see the structure, yeah, the symmetric structure is used here. Yeah. Otherwise, some people may ask, why you use that t minus tau, right? Yeah. So in math, the symmetry is very important. The structure of symmetry is very important. Yeah. So many special operations, so you need to consider the symmetry property. Okay? Yeah, here in this convolution, there is a symmetry structure built inside this convolution operation. Yeah. All right. Yeah. Then the convolution theorem. Yeah. Two functions f and g satisfy assumption in the existing theorem in that. Yeah. So what's that? So here, because let me translate the sentence. Yeah. Yeah. Because here, this assumption. Yeah. 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 That because we need to take Laplace transform, right? Laplace transform f, Laplace transform. First thing we need to make sure their Laplace transforms exist. All right? So we know that inequality, right? Yeah. So this inequality, the absolute value of s less than or equal to, yeah, yeah, because here there is a variable t. Capital M constant times e to the k t, yeah, yeah. So another constant, k is another constant. If there exists capital M constant, k constant, such that this inequality true, yeah, let me write M1, K1, okay? Yeah. Then its Laplace transform exists. Yeah. For G, similar, okay? G function, this time we have capital M2, e to the K2t. Yeah. Another pair of constant, M2 and K2. Then their Laplace transforms exist. Yeah. All right, then we can consider the product capital H function equals capital F times capital G. Yeah. Is the transform of little h given by the convolution operation. Yeah. So that's so now, yeah, that answer, this question mark should be the convolution. Yeah. So the answer is F star G convolution operation. Yeah. Yeah. And then later, after the midterm, we will learn Fourier analysis. So Fourier transform also has this property. has this property. Yeah. 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 Very nice property. Yeah. Yeah. Next, we need to apply this property to solve, some questions. Yeah. This tool, we treat this as a tool. This property, convolution operation, and its properties. So that's some nice tool we can use, to solve Laplace transform related questions. Yeah. All right, let me show you some examples. Yeah. Example using convolution theorem. Yeah. Yeah. The first example, we want to verify. Yeah. First, we want to use a simple example to verify that convolution theorem. Yeah. Yeah. Because here, I do not give you the proof. Yeah. I do not give you the proof. Yeah. But let us use a simple example to verify it is correct. Yeah. Yeah. Because we can, so our goal, we want to calculate the inverse Laplace transform, okay, to find little h of t. That's the goal, inverse Laplace transform. Yeah. Without using convolution, we can do we can find it, right? Yeah. So the first way we find its inverse Laplace transform without using the convolution theorem. Yeah. Then the second time we apply convolution theorem. Now we want to compare. If they are the same, so we verify. Okay, we use this example to verify this theorem. All right. Yeah. Then to inverse Laplace transform, you see the denominator product of two factors, right? Yeah. So remember the split. Yeah. So here, I ask you to get used to that. How to split fraction with the denominator as a product of two factors. Yeah. Here we can do a practice. Yeah. Yeah. Denominator of, because when we do the split, here I show you, one fraction minus another fraction. Yeah. The first fraction, we should use a smaller factor. The value should be smaller. Yeah. So that is 1 minus s minus a. Okay? The second fraction, 1 over s. But after that, because the numerator may not be 1, so you need to, calculate the numerator. When you do the common denominator, the numerator. Yeah. Numerator is a, so you need to multiply 1 over a to make the numerator to be 1. Yeah. All right? Yeah. Old way. So our old way. So let's do the split. So now based on that, so you get that. Yeah. Yeah. Otherwise, every time you get stuck. Yeah. Or some students just apply the partial fraction way. Yeah, you can do it, but usually you need to use more time. When you use the partial fraction way, you need to think about how long do you need. Yeah, you need several minutes. Yeah. But if you can do the split in this way, you can practice, practice, right? Yeah. Until you feel very comfortable, then you can save several minutes. Yeah. Yeah. In the test. Yeah. So it's very valuable. Because in the test, you may need to split the fractions like this several times. You can see, probably you can save 10 something minutes. That's a lot. 10 something minutes. That equals one question. Okay? When you have 10 something minutes, you can solve one complete question. Okay? Yeah. So that's why, using some shortcut way. Okay, all right. Yeah. So then we take the inverse Laplace transform linearity Yeah, so then shifting theorem. Yeah, the other one we know is 1, right? Yeah, so then, you know, first shifting theorem. Yeah, so we know that first shifting theorem. Okay, yeah. So you get that, because second one is 1, first one you need to multiply that e to the at. Yeah. Yeah. So that's the first way. Yeah. Second way, we need to use this convolution theorem this time. Yeah. All right. All right, new way, yeah, because the structure is a product of two functions, right? You can treat it as a product of two functions. So f function, g function, yeah? So it's a product of two functions. And f function, you can find it easily. G function, you can find it easily, right? So capital F, capital G, yeah. Inverse Laplace transform, yeah, yeah. H equals F times G, yeah. Little f, inverse Laplace transform, yeah. So you apply first shifting theorem on, yeah, so here, yeah. Because f of t is 1, yeah. So first shifting theorem. Then g function is just 1, okay? Little h, you need to calculate the convolution of these two functions, little f and little g. Yeah. So that's little h, yeah. F star g, by definition of the convolution. Yeah. Here we do not mean this is easier, but here we for verification, right? It does not mean the second method is easier than the first one. We don't want to say that. Yeah. Yeah. Probably a little harder. You need to do more calculation. Yeah, not easier. Yeah. For the verification, yeah, so we want to check it. Yeah. Then, yeah, the product of these two functions, not very easy. So you can find it, the integral. Yeah. Integral, now you compare the same, right? The old way, yeah. Same result. So now you have the confidence. Yeah. So you have the, after this simple verification, you have the confidence. So that this convolution theorem, yeah, you believe it's correct. Yeah, yeah, yeah. The proof is not that hard. Yeah, the proof, yeah, it's not that hard. Yeah. Okay. Yeah, but here we don't want to do that. Yeah. All right. Then another example. Yeah. Another example. Yeah. This time we want to calculate the inverse Laplace transform of 1 over the denominator s squared plus omega squared, parenthesis square, another square. Yeah. Another square. So here you can, this time you can imagine, if you do not apply this convolution theorem, it's not easy, right? Using our old way, yeah, because denominator, the structure is a square of a function. Yeah. From our basic formula, we do not have any formula like this. Yeah. So from our basic formula, yeah. If we ignore the square, then we know there is a basic formula for it. Yeah. But here we need to add that square, okay, back. So yeah, here, because Laplace transform of sine function, we have this formula. Yeah, but denominator, we need a square of it. Okay? But after we learn this convolution theorem, now it's a product of two sine function. Yeah? Yeah. So here, capital F and the capital G, these two functions are the same function, equals what? 1 over omega times omega, yeah. S squared plus omega squared. Okay? Yeah. So there, little f, little g, the same function. Okay? Little ft, little gt, same function, but you need to do convolution to get the original little h function. Yep. That's the convolution theorem. That's the convolution theorem. But to calculate this function, you need to apply the definition of the convolution. Yeah. All right? Yeah. Yeah. So here. Yeah. So we can do it. If you like, we can do it. Yeah. All right? Yeah. But just you need to calculate certain integral. Yeah. Certain integral. Yeah. Yeah. You need to make some effort. Oh, sorry. I promised I post that formula file. I forgot. So this time I definitely need to post. Yeah, because you can use that in your midterm. Yeah, you can use that in your midterm. Yeah. All right. Yeah. Try to save your time in the midterm. Yeah. All right. More understanding on convolution. Yeah. Basic properties. Yeah. First, so the two functions are commutative. Yeah. Commutative. If you commute, okay, then the same. So we call it commutative. All right. So this is a commutative law. We call it commutative law. Yeah. Then the second, yeah. So this one we call it distributive law. Yeah. Parentheses. We can distribute. Okay. The first function can be distributed to all the terms. Yeah. Here we inside parentheses we have two terms. If you have three terms for any number of terms, you can do this kind of distribution. Yeah. Like this. Yeah. Then another law, yeah, associative law. Okay? Yeah. Yeah. So you associate the first two or the last two, you know, in different ways, the result is the same. Yeah. So that's the basic properties of convolution operation. Yeah. All right. Then zero, yeah, any function, if you do the convolution with the zero function, you still get a zero. Yeah. So that's very easy to see it. Yeah. All right. All right. Unusual property of convolution. Yeah. So all the above properties looks quite normal. Yeah. Yeah. Nothing is special. Yeah. Yes. So everything is as expected. Yeah. But unusual properties. Yeah. Something, you know, yeah. There is some special properties. Yeah. Yeah. So let's see. Yeah. The first one, you do the convolution between any function with one function 1. You won't get the same function. Yeah. You won't get the same function. Yeah. Yeah. Yeah, because f star 1, by the definition, it is this function, yeah, integral of the original f function. It could be quite different from the original function. Yeah. It cannot be the same. Yeah. And its derivative is f. Yeah. All right? Yeah? So that's first unusual. The second unusual, f star f. Yeah. Yeah. Because if you look at it from its form, that star looks like multiplication, right? You know, some people may get confused with the multiplication operation. But for the multiplication operation, f times f itself, you get a non-negative function, f squared. Now, but here it's not. F, you do the convolution with itself. Yeah, you get another function, but that another function is not necessarily a non-negative function. Yeah. Here we can just do a simple example. Yeah. F function equals 1 minus t. Yeah. the convolution. Yeah. We take integral, we get this function. Definitely this function is not a non-negative function. You cannot prove it cannot take the negative value, right? Yeah. So you can, plug in some special value, yeah, to make it a negative. Yeah. It's very easy, you can take some value. Yeah. You get a negative. Yeah. All right? Yeah. Next, integral equations. Integral equations. All right. Solved Volterra integral equation of the second kind. Yeah. So there's some special problem. Yeah. So this kind of equation needs to be used. Y original function, the second term you need to take integral. So not derivative, integral. Yeah, but here you can see the structure is a convolution structure. Yeah. Equals t. Yeah. The question, how to find original function? Yeah. All right. Yeah. So let us, this slide. That's the last slide of today. Okay. After finish, so we complete today's class. Yeah. So here, let us try to understand the structure here. Yeah. Yeah. Think about if we do not know anything about the convolution operation. Yeah. If we know nothing about convolution. When you see this equation, how to solve? Yeah. Extremely hard, right? Yeah. If we know nothing about the convolution, then we don't know how to solve it. Okay? Yeah. Yeah. All right. But after you learn the convolution, especially the convolution theorem is important here. Yeah, we need to use convolution theorem. Yeah. Yeah. Then we can solve it easily. Here you can see the tool, the problem solving, the tool is so important. If you don't have the knowledge, if you don't know that tool, extremely hard. Yeah. Yeah. Even for many smart mathematicians, when they do not have the appropriate tools, they couldn't solve, some very smart, some problem. Yeah. Yeah. Here I know one example. So I read some number theory book. It's called Elementary Number Theory. Elementary Number Theory. Small booklet. I read. When I read that, I noticed one story. Yeah. So I got impressed a lot. Yeah. Big mathematician Euler, right? Yeah. Yeah. Some people rank Euler as top 5. Okay, yeah. So all the mathematicians, in history, among top 5. So then no argument. Yeah. All right. So he then once Euler he discovered some property, some number theory property, some expression divide. Yeah, so I couldn't remember exact. Well, yeah, just some formula, then divided by, something like so n to the a minus some n minus 1 to the b, something like that. Then it's a multiple of some other. And he discovered that property, and he verified, plugging certain numbers, all correct. Yeah. Then he wrote, well, so I found a, great property, but I don't know how to prove it. Yeah. I don't know how to prove it. Okay? Euler, so smart. Yeah. But that special property, he couldn't prove it. But he wrote, somewhere, letter, some, Yeah. But later, Fermat, Fermat, right? Another big mathematician. Fermat, ER, right? Fermat. Whatever, right? Fermat, another mathematician, not as good as Euler. If we look at the production, Fermat should be much lower than Euler. Okay, but also good, also very good mathematician. Fermat discovered a theorem called Fermat-Little theorem. Fermat has a big theorem. Big theorem, and then there is a little theorem. Fermat's little theorem. Fermat's little theorem. Little theorem. Another nice theorem in number theory, very, very important. Fermat discovered, after some years. Then apply the Fermat's little theorem. This question, one line, can prove. Just plug in. Okay, choose some special numbers. Plug in. One line proof from Fermat's little theorem. So this story tells, if even for a mathematician as good as Euler, if he does not have the appropriate tool, here we treat Fermat's little theorem as a tool, right? Some special tool in problem solving. He cannot solve. Some problem cannot solve. Here we have the similar situation. Here we treat convolution as the special tool, okay, with its properties. Okay, convolution operation with its properties. That's the powerful tool. If you do not know that, then this problem you cannot solve. Okay, so that's the similar situation as the Euler situation. Okay, all right, So so let's leave the next time. Then the solution should be straightforward. So next time we just refresh our memory. We complete the remaining part of this part C. All right. That's it.